Welcome to our quantum deep dive. Today we're venturing into some really cutting-edge territory in quantum physics. Highly theoretical, but fascinating. We're talking about pioninos. Now, if that name doesn't ring a bell, don't worry. You're about to get, well, a deep dive into what could be a major concept down the line. Our guide today is an essay by Jorgo Schneeppert titled Pioninos Hypothetische Teilchen in der Quantenphysik. And our mission really is to unpack this. What are pioninos? Where did the idea even come from? What could they do for future quantum tech? And maybe crucially, why are they so hard to pin down? We want to pull out the key ideas so you can get up to speed quickly on this pretty mind-bending concept.
Yeah, and it's important to stress we're really stepping into the hypothetical here. These aren't particles sitting in a detector somewhere. They're ideas born from our complex models trying to explain things happening right at the edge of what we understand about the quantum world. It might seem abstract, but exploring these ideas, even theoretical ones, is, well, absolutely vital. It pushes science forward, opens new doors for research. It's how progress happens, really.
Okay, let's start right there. The essay calls pioninos hypothetical quasi-particles. Hypothetical. Okay, that means theoretical for now. But quasi-particle, what does that mean here?
Right. Hypothetical, yeah, it just means it's predicted by theory, no direct proof yet, like a suspect in a case, maybe. We have reasons to think it exists. Now, quasi-particle, that's a bit different. It's not a fundamental budding block like an electron or a quark. Think of it more as an emergent phenomenon. Imagine ripples on a pond. The ripple isn't a single water molecule, right? It's a collective movement, a disturbance in the water. Quasi-particles are kind of like that. They're collective excitations, patterns that show up because of really complex interactions, these many-body effects within a quantum system, especially when you have lots of, say, fermions or bosons strongly interacting.
Okay. So it's the ripple, not the water drop. That makes more sense. It's the collective behavior acting like a particle. And the name pioninos, it sounds specific. Is there a story behind it?
Oh, definitely. The name's quite clever, actually. It comes from pion, that's a fundamental particle, a meson, involved in the strong nuclear force holding atomic nuclei together. And then ino is a common suffix in physics, often used for hypothetical partners or derived particles. Think neutrino, or maybe more theoretically, gluino. So Pionino suggests something derived, something related to the pion, maybe playing a similar role but in a different context, like condensed matter systems, not atomic nuclei. It hints at its nature.
Okay, derived, related to pions. But if they're emergent, sort of collective effects, how do you even describe them mathematically? Physics always comes down to the math, right?
Absolutely. And the math is where the elegance often lies. You can describe their dynamics using something that looks like a wave equation, basically how they move and change over time within their environment. But the real fingerprint, the key identifier, is what's called the dispersion relation.
Dispersion relation.
Right. Yeah, it's crucial. It tells you exactly how the pianino's energy relates to its momentum. Think of it like its characteristic signature. It involves things like an effective phase velocity, how fast it seems to move in the medium, and an effective mass. And that mass isn't fixed. It's modified by all those complex interactions happening around it. Understanding this relation is vital for figuring out how they might behave or how we could detect them.
So if they have this unique mathematical fingerprint, how do they stack up against other quasi-particles we know about, like excitons or plasmons? Are pioninos really something new?
That's a great question because the quantum world has a whole zoo of these quasi-particles. And yes, pioninos seem distinct. Take excitons. They're specifically a bound pair of an electron and a missing electron. Very defined structure. Pioninos are thought to be more complex, these collective excitations and strongly correlated systems, much fuzzier perhaps. Then you have Majorana fermions. They're super interesting, they're fermions, but they're their own antiparticle. Very exotic. Pioninos, on the other hand, the essay suggests they could possess bosonic properties. Bosons behave very differently from fermions.
Like allowing multiple ones in the same state.
Exactly. And then plasmons are basically collective wiggles, density waves of electrons, usually related to charge oscillations. Pioninos might be more intricate, maybe involving a combination of charge and spin dynamics. So yeah, the paper makes it clear, pinning down their exact classification. That's still very much an active research question. They could be quite unique.
Let's go back to that pion connection. If they're in fundamental pions, what's the real analogy there? Is it just the name hinting at a mediating role?
It's definitely deeper than just the name. The analogy is really in the mathematics and the function. So fundamental pions carry the strong force between protons and neutrons in a nucleus, right? They mediate that interaction. The idea here is that pioninos, within these strongly correlated electron systems, could assume a similar mediating role for interactions there. They could be the messengers carrying some effective force within the material.
Okay, so mediating interactions inside a material, analogous to pions in a nucleus.
Precisely. And theoretically, you might even describe them using tools adapted from nuclear physics, like effective chiral perturbation theory, which was originally developed for pion interactions. It's like taking a successful blueprint and adapting it. And the really exciting prospect mentioned is the potential for strong coupling between pianos and magnetic or electronic excitations in materials.
What would that mean practically?
Well, it could lead to totally novel quantum phenomena. Imagine being able to control a material's magnetic properties or how it conducts electricity just by manipulating these Pionino excitations. That opens up huge possibilities for new types of materials and devices.
Okay, so they're emergent, maybe mediating interactions, possibly controllable. What about their core quantum properties? Do they do the usual quantum weirdness, like wave-particle duality?
Oh, absolutely. If they're quantum entities, they have to. They're expected to be both wave and particle-like objects. Their wave psi would be described by a quantum wave function, governing their probabilities and dynamics. And depending on whether they lean bosonic or fermionic, their behavior could be captured by something like a modified Schrödinger or Dirac equation, the bedrock equations of quantum mechanics.
Right.
And that dispersion relation we talked about, that's fundamental here, linking the wave property, energy, frequency, to the particle property, momentum. It defines their quantum identity.
Which brings us to the big one for quantum tech. Can they do superposition and entanglement? Because that's the magic sauce for quantum computing, right?
Exactly. And the theory says yes, absolutely. They should be able to exist in superposition, meaning a combination of states at once, like being both state 0 and state 1 until you measure it. That linear combination idea.
Okay, crucial first step.
And even more critical, the essay suggests they could become entangled with other quasi-particles. That spooky connection where measuring one instantly affects the other, no matter the distance.
Wow.
That's the engine for quantum algorithms and secure communication. So yes, having those properties makes them extremely interesting candidates for future technologies.
So if they have these properties, how would they, interact with everything else in a quantum system? Could they mess with existing fields or even change how a whole material behaves?
They absolutely could. The theory suggests they'd couple with other quantum fields, electromagnetic fields, phononic fields, which are like sound vibrations in the material's lattice, or the electronic fields themselves. And this coupling wouldn't just be a tiny effect. Their presence could strongly influence macroscopic properties.
Like what, for example?
Well, they might change the electrical conductivity, maybe making a material a better or worse conductor. They could interact with magnetic moments, affecting its magnetic behavior. They could even impact quantum coherence itself.
Impact coherence. How?
It could go both ways, potentially. They might introduce noise and cause decoherence, which is bad for quantum computing. Or perhaps they could be harnessed to enable new kinds of quantum logic gates, new ways to perform operations in a quantum computer. That's the exciting possibility.
And could we control them from the outside, like poke them with a magnet or something? And how would we even spot their spectral signature?
Good questions. Yes, external fields should affect them. If they have charge or a magnetic moment, a magnetic field could force their energy into specific discrete levels like Landau quantization for electrons. That would be a clear sign.
Ah, distinct energy steps.
Right. And an electric field could push them around if they're polarizable. As for spotting them, we'd look for their spectral signatures. Techniques like scattering experiments bouncing neutrons or light off the material or optical spectroscopy could reveal characteristic peaks or dips in the energy spectrum. The position of the peak tells you the Pionino's energy, and its width, mathematically described by this function omega, tells you about its lifetime, how long it sticks around before decaying. Finding those specific signatures would be key evidence.
Okay, now the really exciting part. Let's assume, for a moment, they do exist and have these properties. How could Pioninos actually change the game in quantum technology, especially quantum computing?
Right. This is where the potential payoff is huge. They could potentially serve as qubits, the fundamental bits of a quantum computer. To do that, they'd need to support that long-lived, controllable quantum superposition we talked about, being able to put them in a mix of states, like pi wrangle, alpha 0 wrangle plus beta 1 wrangle, and keep them there reliably.
And how might you build a qubit from a Pionino?
Well, the essay suggests a few routes. If they emerge in superconductors, they might form the basis for superlight-toned qubits, superconducting qubits, a leading current technology, but maybe with pianinos offering some advantage. Or, if they have special topological properties, meaning their quantum state is protected by the overall structure, making it robust against local errors.
Ah, the topological protection idea.
Exactly. Then they could be used for topologische qubits, which are inherently resistant to noise. That's a huge goal. Or if they interact strongly with light, maybe optische photonische qubits, different potential platforms.
And what would make Pionino qubits potentially better than what we're working on now, like trapped ions or those superconducting circuits?
Several potential big wins. First, possibly longer coherence times. If they interact weakly with the environment, they could hold their quantum state for much longer, allowing for more complex calculations. That's a major bottleneck right now.
Okay, longer coherence, huge. What else?
Increased scalability. If they naturally occur in solid-state materials and are relatively easy to create and control in large numbers, it might be easier to build massive quantum computers compared to, say, trapping individual atoms.
Makes sense. Easier manufacturing, maybe?
And that resistance to decoherence, especially if they turn out to be topological, that inherent robustness would drastically reduce the need for complex error correction, which is another massive challenge for current quantum computers.
Longer life, easier scaling, less noise.
Yeah.
That's quite the wish list for quantum computing. What about secure communication? Quantum cryptography, could they help there too?
Absolutely. They could be central to secure quantum networks. If they can carry stable quantum states reliably, they could act as information carriers. You could use their entangled states, like that Bell state, B over Wrangle E1, 1 Wrangle B plus 1 Wrangle 0 Wrangle, to send information securely over long distances. Any attempt to eavesdrop would disturb the entanglement and be instantly detectable.
The foundation of quantum cryptography.
Exactly. Their entanglement could directly enable robust quantum key distribution, QKD protocols, like using Phi plus Wrangle plus 11 Wrangle, for sharing unbreakable encryption keys. And again, if they're less prone to decoherence, that means lower susceptibility to disturbances, potentially giving us increased range for quantum key transmission, and maybe even inspiring completely new cryptographic methods we haven't thought of yet.
Okay, the potential is clearly enormous, almost transformative. But how on earth do you actually find something like this? Where do scientists even start looking for a hypothetical quasi-particle?
Yeah, that's the multi-billion-dollar question, isn't it? It starts with the theoretical predictions. The models suggest they're most likely to pop up under pretty extreme conditions. We're talking strongly correlated quantum systems, exotic materials where electrons interact very powerfully, or ultra-cold quantum liquids near absolute zero, maybe even in high-energy plasmas, places where quantum effects dominate and things get weird.
So not exactly everyday condition.
Not at all. And detecting them would likely be indirect. You'd use techniques like inelastic neutron scattering or Raman spectroscopy. Basically, you probe the material with neutrons or photons and look for tiny energy shifts, a signature that a Pionino was created or destroyed.
Looking for specific energy fingerprint again.
Precisely. Or in quantum Hall experiments, maybe you'd see unexpected plateaus in electrical resistance under strong magnetic fields. That could hint at new kinds of quasi-particles. There's even a long-shot possibility for particle accelerators like the LHC. You wouldn't see the Pionino directly, but maybe missing momentum energy in collisions or strange bumps, anomalous spectral lines in the data that don't fit known particles.
Wow, even particle colliders.
It's less likely for a quasi-particle, but possible if they couple somehow. More realistically, ultra-sensitive quantum sensors, like SQUIDs, which detect tiny magnetic fields or atomic interferometers, might pick up the subtle disturbances caused by pianinos existing within a material. It's really about looking for subtle anomalies.
It sounds like searching for a whisper in a hurricane. What are the biggest roadblocks to actually proving they exist?
Oh, the challenges in measurement are huge. First off, thermal noise. At normal temperatures, atoms are jiggling around like crazy, creating a background roar that would drown out any faint Pionino signal.
So you need extreme cold.
Exactly. Cooling down to millikelvin temperatures, just fractions of a degree above absolute zero, is often essential.
Ptex Roshan Propto Efrax Sminger. Then there's just the limits of our instruments. Maybe they aren't precise enough yet. A massive problem is simply not knowing where to look, the uncertainty about the existence region. What materials, what specific conditions.
Could be looking in the wrong place entirely.
Right. And decoherence effects. If pianinos are very short-lived, They might vanish before we can reliably measure them. Plus, you have the problem of interferences with other quasi-particles. Other collective effects in the material might produce similar-looking signals, making it hard to be sure you found a Pionino. The best strategy is often triangulation, trying to see consistent evidence using multiple different measurement techniques.
Okay, so the hunt is tough. Looking ahead, beyond just detection, where does Pionino research go? What's the future path? It's really a parallel track of theory and experiment. Theoretically, we might need new concepts, maybe nonlinear effective theories, mathkiel frac 1, mathkiel frac 1 2, pri 1 2, per p 2, please c plus gp 4 plus, to capture their complex behavior better than current linear models. And exploring their role in quantum information processing, maybe as these error tolerance quasi-particles, is a big theoretical push. And guiding the experiments, we need better simulation models, using powerful techniques like DFT, quantum Monte Carlo, tensor networks to predict where and how Pioninos might appear, giving experimentalists better targets.
And if they are finally confirmed, what are the dream applications of big technological innovations we might see?
Well, we've touched on them, but it's worth repeating. Quantum computers are the big one. Better qubits, maybe coupling elements. Quantum communication carrying secure information further and more reliably. Quantum metrology using their unique properties for ultra-precise measurements. And one really intriguing area mentioned in the essay is the potential impact on superconducting materials. If Pioninos interact with Cooper pairs, mathkiel pese, the electron pairs behind superconductivity.
What could happen?
It could potentially lead to new forms of high-temperature superconductivity. That would be revolutionary lossless power transmission, powerful magnets for medicine and fusion. A massive technological leap.
Wow. Okay, so the stakes are incredibly high. But despite all that potential, what are the big, nagging, open questions that researchers are still grappling with?
There are quite a few fundamental ones. Are Pioninos truly distinct, independent quasi-particles, or just, a different way of looking at complex interactions we already sort of understand? Could they hint at deeper physics, maybe emerging from more fundamental interactions not yet considered in our standard models?
Like pointing towards new laws of physics.
Possibly, or at least new regimes. And the ultimate practical question, are our current measurement methods even sufficient to nail this down unambiguously? Especially given how sensitive these things might be to environmental disturbances and the inherent precision limits we face. These are the big unknowns driving the research.
It's incredible. The whole concept of Pioninos really stretches the limits of what we think we know about quantum physics. It shows just how much might still be lurking in these complex quantum systems. So let's try to sum up. Pioninos, they're hypothetical, they're emergent quasi-particles, sort of collective wiggles in a quantum material. They're theorized to have amazing quantum properties, superposition, entanglement, which gives them this huge potential for quantum computing, secure communication, maybe even new superconductors. But, and it's a big but, actually finding them, proving they exist. That's a massive experimental challenge right now, which leaves us, and you, with a pretty deep question to ponder. Could Pioninos be that missing piece we need for the next generation of quantum tech, or could find them and actually rewrite some fundamental rules of the universe? Thank you for joining us on this quantum deep dive exploring the thought-provoking work of Jürgen Schneppat on Pioninos. If you want to dig into the original essay yourself, you can find it over at schneppat.de. Until next time, keep diving deep.